in Mathematical Modeling and Simulation, a master's degree in Defense and Strategic Studies, and has undergone an executive management program at the IIM Lucknow. He's had the honor to head the Marine Engineering departments of several frontline warships of the Indian Navy. His shore appointments included leadership roles in operations, maintenance, supply chain management, and quality assurance. He was instrumental in steering the development of mathematical model for the main propulsion control simulators and diesel engine health monitoring software during his deputation to the DRDO. He subsequently joined L3 Communication, heading the Marine Automation Program prior to his elevation as whole-time director. He is currently a senior consultant to TCS in the field of marine automation. He is a strong advocate for use of mathematical modeling techniques in the warship building industry. I would now kindly request our chief guest to deliver the opening address.
Good evening to everybody, and thank you, Captain Girish, for the nice introduction. I should commence by saying that it's really an honor to be a part of this INA session today, and specifically so the topic which is scheduled for this particular session, that is the propulsion systems integration, a topic which has been very close to me, and I have been working in this field for quite some time, both in the technical capacity as well as the business role. So that way it's a sort of a homecoming for me, and immense sense of satisfaction to be a part of this kind of session. I should say that the topic which has been chosen for today, it's one of the I will say a very interesting topic, and also a topic of a large interest, because this shaft alignment is a very key aspect of the entire shipbuilding program, and particularly so the shaft alignment aspects are taking more and more complexities with a large number of varieties in the kind of propulsion systems that are coming in. So it is no more a single propulsion system of whether a diesel or a steam or any other type of thing. It's more of a combination today that is happening. So lots of inertias that play into the scheme, a lot, and coupled with the changes in the hull architecture, which are also going on in parallel in order to make those hull profiles more and more efficient at sea. So I would put it that the shaft alignment is taking a more and more complex role in the shipbuilding program, and it's only apt that the kind of technologies that are being used in order to ensure that the customer has almost 100% confidence of the performance of the propulsion system upon the launch the very first time, which is what is the ultimate what we all aspire to. Use of mathematical techniques and all the tools that are available in the market today in order to overcome what is, I will say, primarily a highly empirical oriented kind of a job. This is something is a very good step in the right direction, and I'm sure Mr. Kawade, who is now taken up this topic, and likes of him, many who are working in this field, this is the right time to be putting the right thrust for this kind of a topic. And with these few words, I would like to close my opening address. Thank you very much for the opportunity.
Thank you, sir, for your valuable insights. I would now like to share the procedure that we would adopt during the course of the session. Participants are kindly requested to type in their comments and queries in the chat box at any time during the talk. The microphones of these participants would be unmuted sequentially to enable them to field their questions, stroke thoughts on completion of the presentation. They are requested to turn their camera on for this duration. The participants are requested to kindly mute their mic when not speaking. Our invited speaker for this session is Mr. Mahesh Kawade, Chief Manager, Design at the Masgon Dock Shipbuilders Limited, Mumbai. He is a mechanical engineer with specialization in naval architecture with around 2 decades of experience in the industry. He has been a member of the design team of warships. He is presently part of the forward design group and leads the team for preparation of requirements document for new build vessels. He is a member of the propulsion system integration team at NSTL. Mr. Kawade is also involved in providing technical solutions to ongoing projects in the areas of computational fluid dynamics, shaft analysis, apart from other challenges in the field of naval architecture and mechanical engineering. Shaft alignment and health of shaft lines on board ships are important facets that determine the availability of ships. Optimization of timelines in ship construction without compromising on the requirements is a delicate task that mandates due diligence. The paper being presented by Mr. Mahesh Kawade is based on a revised alignment procedure introduced by his team in determining the lay of the shaft line in dry dock itself with the aid of software tools to predict final deflection, thereby enabling a drastic reduction in shipbuilding timelines. Thank you. Now, I would kindly request Mr. Kawade to present his address. Thank you.
Good afternoon, everyone. So the today's topic is propulsion system integration, process innovation through alignment calculations. As Captain Girish sir has brought out that there is always conflict between naval arcs and marine engineer, I think I am the best person to bridge gap between the two faculties. And I have done that in Masgon Dock Shipbuilders Limited. I have got naval arcs to work for me to my requirements. So the presentation will proceed as is presented on the screen. Introduction to the problem, background, then problem definition, probable solutions, and development of innovation, methodology for defining the process, innovative process through the support of design team by doing alignment calculations so that the entire alignment process is monitored, estimation of elastic line at various loading condition, then cost benefit, and then finally conclusion of the session. So shaft propulsion, shaft line alignment. The shaft alignment is optimal positioning of shafts and bearings relative to the reference axis that is established in on slipway to achieve optimal bearing load distribution that satisfies all operating conditions of the ship. So optimal bearing distribution will ensure maximum bearing life. A good static alignment is required for trouble-free dynamic operation of the vessel, of the propulsion shafting for efficient power transmission. The objective is that the alignment remains within the tolerance band for vessel in varying loading condition as well as temperature variation due to ambient conditions, which is more prominent in our tropical countries, as well as due to the increase in lubricating oil temperature, as some of the bearing locations may be located above the fuel double bottom lubricating oil tanks. So all these factors are to be taken into account. The tolerance band is between the light ship and fully laden condition, the loading condition. So as shown on the screen, the picture shows the fully laden condition and light ballast condition. The left hand is a pictorial view. The right hand shows the tolerance band of hull deflection values. A good shaft alignment has to ensure stable and robust operation within the full range of hull deflection values. So disturbances that affect shaft alignment are hull deflection as projected above. And in our case, as we are living in tropical country, we need to also take into account this thermal rise in lube oil temperature and ambient conditions during shaft alignment activity. So this is the life cycle for shaft alignment. Preliminary sighting is done on slipway. Post completion of the major welding work, that is outfitting of all the blocks. Post full hull fabrication, we undertake this pre-alignment condition, and maybe we will be welding A bracket and all the hull appendages, like if P bracket is there, also P bracket on slipway itself. Then final shaft axis is done in dry dock. That is where the conflict begins between naval arcs and marine engineers, as this axis has to be passed on to marine engineers from hull people. And final alignment is done in afloat condition, where inside the offsets of inside bearings are adjusted to suit the optimum elastic line. In basin trials, post basin trials, after that basin trials are conducted at low RPM, and post basin trials we validate the elastic line through load checks for inside hull bearings, and with the help of filler gauges in case of underwater hull bearings. Same activity is repeated post sea trials before delivery of the vessel. So this is the layout of propulsion system, showing from prime mover to propeller. So power is transmitted through reduction gear and thrust block to propeller. All these support bearings, plumber bearings are located in between, which makes the beam to be a statically indeterminate beam and has to be solved through finite element software. So the present conventional procedure is final alignment is done at 85% of standard loading condition, that is in afloat condition. This is where we get actual hull deflection values at 85%, and inside hull bearings are optimized for their offsets to arrive at a optimum elastic line. The alternative method is to do the final alignment in dry dock through shaft designer software by using hull deflection values to get the bearing loads at 85% standard loading condition and give the offsets in dry dock itself. However, this sounds to be a calculated risk, but if we incorporate this risk, we have certain advantages of this, which we'll see in the coming slides. So this is conventional shafting procedure. It is done in afloat condition. Underwater bearings like A bracket and stern tube bearings, we fix in dry dock during final shaft axis, and we keep PB2, PB1, MTB open for optimization within the limits, so that optimum elastic line is established in afloat condition. This is conventional procedure. What we propose is to do the final alignment in dry dock itself by giving offsets to the bearings PB2, PB1, MTB at 85% standard loading condition, and then validate these things, validate the alignment at 85% standard loading condition for any changes which are outside the limit of the calculations. So this is the activities involved in conventional shafting procedure. Slipway, we establish pre-alignment condition. Then welding of appendages is done in line with reference shaft axis, and the vessel is launched. Then after 6 months in dry dock, we commence with shafting activities again. These are the activities involved in dry dock for conventional, and we keep optimization part in afloat condition, which is achieved after 18 months of dry dock. So this is the idle period for propulsion, and this needs to be optimized. So this is critical because due to non-confirmation of alignment up to MTB, the below part of RG and GT alignment, GT uptake and intake fabrication, intake insulation, all this part is kept on hold till 18 months. So that is why we need to compress this period, so that we can do final alignment in dry dock itself and get the work fronts open for all these activities, which will result in reduction of build period of the vessel. This is the main objective of the study is to make an attempt to compress overall conventional build period of a vessel by 6 to 8 months. This will be achieved by completing propulsion shaft line assembly and final alignment securing activities in dry dock itself, against an afloat condition where we have to wait for attending 85% of standard load condition. So this is the timeline of a build period of a ship. From keel laying to launching, it takes 12 months. So dry dock and afloat timeline that is shown on the screen is for shaft line activity. In conventional procedure, there is a lead period of 18 months as shown in the previous screen between dry dock and afloat conditions. So that is adding to outfitting activities of 6 months. And lead time for BT, CST and delivery is 12 months. So total build period as is now, it is 66 months. But with the innovative procedure, if we can do this activity, shaft line activity, in a sequential way from launching dry dock to in dry dock, skipping afloat part, and that way we can compress the build period by 6 months. Outfitting and setting to work will be reduced by 6 months. In a way, some of the outfitting activity can be taken up in dry dock itself, and can be effective planning can be done. So the methodology that is followed is in phase 1, we do shaft line alignment calculations for dry dock using shaft designer software. The yard has its own calculations, and also we have the calculations given by OEM. We do the final alignment of shaft line in dry dock itself. We give offsets to plumber blocks and MTB as per the OEM document, and then we measure the bearing load in dry dock condition. In phase 2, what we do is we need to have hull deflection values at undocking condition, which is less than 85%, maybe somewhere around 66%, for which we take hull deflection values, introduce it into the shaft designer values and shaft designer software finite element calculations to get bearing loads at 66% of loading condition. This is how we do the calculation part. Now coming to the validation part. So we simulate the hull deflection values by loading the tanks adequately to achieve the displacement, trim and LCB at 66% loading condition. And then we measure the bearing loads on board by using hydraulic jack method and compare it with our calculated values. These values are not given by OEM, since this is an intermediate condition. OEM has given 85% alignment values. So in phase 4, we compare the hull deflection values at 85% of standard loading condition and bearing loads at standard loading condition with 85% after the vessel reaches 85% standard loading condition. All these values, if they are within the limit tolerance band given by OEM, then the alignment is validated. And so this is the shaft line model. We have shown only propeller loads and moment. Then OKF, OKC forces at OKF, OKC are shown. OKC coupling are shown, and at flanges the forces are shown, and at spacer ring moment and force is shown. Here we have not introduced propeller because in dry dock propeller is not installed. Instead, we have taken propeller loads into account. So this is the elastic line in dry dock. So this is with 0 offset bearings. So it clearly shows that some offset is required, which is given as per alignment calculations. At 85%, the offset is at 85% of standard loading condition. This is the pressure distribution along the length of the bearing for underwater bearings, as load measurement is not possible for underwater bearings. So we have to rely on finite element calculations. The load distribution clearly shows that the shaft rests on every part of the bearing. So edge loading failure is eliminated as per the calculations. This is this is A bracket. This is for aft stern tube and forward stern tube, or aft stern tube, and this is forward stern tube bearing in dry dock condition. Now hull deflection for curve for undocking condition. As during discussion, we are talking about finite element analysis for hull deflection, for calculation of hull deflection, but we have used here our naval architecture practice. Here weight distribution of the vessel is known. From that we get buoyancy curve from Aviva Marine, and weight minus buoyancy will give us moment at different stations along the length of the vessel. So we get bending moment. From bending moment we get M by EI curve, and after double integrating M by EI curve we get hull deflection at various stations of the vessel. These hull deflection values at bearing locations are incorporated in shaft designer software to get the bearing loads. This is the shaft alignment calculation for undocking condition, which corresponds to 66% of standard loading condition. So there is a very slight variation, though here the pattern seems to be same. There is difference in values. Maximum pressure and average pressure is different at 66% and in dry dock condition, 66% and dry dock condition. This is forward and aft stern tube at 66% loading condition. And this is the alignment condition at 85% standard loading condition. This is the shaft line. These are the underwater bearings. A bracket, aft stern tube and forward stern tube bearings. So challenges involved in this are as a prediction of hull deflection at new loading condition, because for OEM we give hull deflections at 85% of standard loading condition, for which he gives us the calculation, and we need to load the bearings at 85% standard loading condition in afloat condition as per his values. But here we have introduced 66% loading condition, and we have validated our results for all the three conditions: dry dock 66% and 85% of standard loading condition. We have used our analytical method of doing double integrating M by EI for calculation of hull deflections. Then second challenge is monitoring and measurement of pre-aligned axis. So this is very essential, as during the course of alignment we need to monitor whether any edge loading is happening. But the calculation might show you the bearing load within the specified limits, but underwater bearings also average pressure may be within a specified limit, but you don't know maximum at which point maximum pressure is there. So if it is at only one end, then in case of Thorndon bearings, hydrolysis failure may happen at low speed, at low shaft speed. And third challenge is very peculiar, which is common to conventional as well as innovative procedure also, that are environmental constraints. That is stern drop alignment. During alignment in dry dock, the monitoring of stern drop, so that you are aware of the zero position, which is usually attained at 2 p.m. in the night. And second, which is not there, that is a lubricating oil temperature, which may result in local deflection of the tank and may impact the bearing load. if the bearing load setting is located above the lubricating oil tank. So advantages of the innovative shafting procedure as listed: reduction in build period of the vessel. So obviously, as we have seen, 6 months reduction is possible to achieve. Then alignment in dry dock is stable, as you have only variable condition in the form of stern drop. After that, inside hull bearings can be just adjusted as per the OEM calculations and giving offset to the bearings. This procedure is sequential, that is, it can be completed in series. You need not break the procedure for 18 months. And better utilization of manpower and other resources, that is planning, can be done properly. Part outfitting can be commenced in dry dock post final alignment. Then installation of deep sea seal at very early stage relieves the yard of preservation cost of the shafting, because shaft rotation is possible at very early stage. And then availability of work for GT intake and uptake, which results in early commencement of these jobs and thereby compressing the build period of the vessel. Thank you. I have finished. I am open to questions, sir.
Thank you, Mr. Kawade. That was a very interesting lecture. You can stop. You can unshare your screen, please.
Yeah.
Thank you. May I request the chief guest to kindly share his thoughts on the interesting lecture?
Thank you, Captain Girish. And first of all, I would like to commend Mr. Kawade for his excellent work that he is doing right now in order to optimize the costs that are associated with the critical evolution of shaft alignment. And certainly, it's a step in the right direction to harness all the available new technologies and tools that are there at our disposal in order to solve this one very complex part of the shipbuilding program. Because once the shaft alignment aspects are set, a number of snowball activities can also be compressed, and the time to delivery can also be, bettered over a period of time, because that is what the customer is really looking for. But then, of course, shaft alignment plays a very critical part in the whole process. And the steps what is now being proposed now in order to complete the task to almost a 90% plus certainty at the dry dock condition itself. It's a step in the right direction, but then possibly being a little pessimist by nature, I see some gaps which are there still that is yet to be addressed, because the environmental constraints which are there in this whole process, that is something which may play a spoil sport at a later date. And the compensations in terms of the mathematical modeling which we will do for this particular aspect of environmental constraints, because this is very non-linear. You don't have really a very great control on this, because the rest of the aspects of it you can still have some control by advanced calculations, and in fact, even I will say the hull loading conditions also. I am not really sure how the meaning, not that I'm trying to be very pessimistic about it, but then trying to just put in my thoughts that the ship undergoes a lot of stress relief during its construction phase. And as and when the machineries are getting installed, a lot of shape change and other things happen. Now, these have ultimately the final effect also onto the shaft alignment. So the environmental constraints which you have indicated in your slide, I hope these are the ones which are being taken, because the hull deflections over a period of time happen in a very different way. If you are in a covered dry dock or you are in a open dry dock, your summer and the winters, periods. So in what periods do you do this, and how effectively does the alignment confidence level, address all these aspects so that you are first time right when you get into the sea? The second aspect is also meaning it's just a matter of a consideration that I'm just suggestion that I'm making is on the particularly so when you are having this multiple propulsion systems and the torsional values which come, although the TV analysis and other things are anyway done as a part of the propulsion systems integration. How does these alignment calculations, meaning the spectrum of the flexibility to take the alignment when the propulsion transits from one type of propulsion to another propulsion, is something which possibly also needs to be factored in. But otherwise, I will say that I would like to express my sincere appreciation of the very thought process that on which Mr. Kawade, meaning as a part of the MDL as such, has gone ahead, because this is the need of the hour. We need to build our ships more faster and with more higher confidence with each passing day. It is just like we will have to reach a stage where we can roll out cars in the assembly line. So this is exactly where we have to be aiming to, and I should commend having you selected this particular topic as one of the most key topics in this entire shipbuilding program. Thank you, and I would like to commend you for the excellent efforts that has been put into your research paper. Thank you.
Thank you, sir. First of all, the first part of your concern was regarding this stern drop that is happening due to temperature variation. So in dry dock, what we monitor this stern drop for 3 continuous days. 3 continuous days we monitor for this stern drop. The aft portion of the ship is loaded with the equivalent weight that is going to come in the aft portion, like steering gear compartments and all those, and we add dummy weights to simulate the actual condition. Then we monitor this the stern drop for 3 days. We take the readings continuously and we establish 0-0 position, which usually comes at 2 a.m. in our country like ours, and that is our reference axis with reference to which we carry out the underwater shafting. And post fixing of underwater appendages, then we go inside. This way we take the care of environmental care as far as ambient temperature is concerned. And for lubricating oil thing, we have done some finite element analysis to see the local structure deflection in the way of plumber this bearing location. So we incorporate these things in design calculations, alignment calculations, and accordingly we set the bearing offset values.
Yeah, I have got some. Sorry, sir.
Yeah. Please go ahead.
Yeah, I have just got some certain things. The envelope of hull deflection and operating conditions is essential. The entire envelope, what are the envelope of hull deflections and the entire operating conditions, is essential to define a set of optimized bearing offsets. That means, what are the bearing offsets? What are the range of bearing offsets that will emerge from the envelope of hull deflections, as well as the operating conditions of the ship. Now, these offsets should enable an acceptable bearing load distribution and shaft bearing misalignment in all conditions of service. I was just wondering, do we evolve this sort of optimized bearing offsets when doing the course of this entire study?
Sir, bearing offsets, this study we have not done, sir. We have not. Okay. We have just got bearing offsets from OEM. And
basically, then what I was just trying to tell is that, you see, the ship has got a various set of loads, right, from dry dock condition to maximum 100% loading. Then yes, you will have different conditions of sea swell. Yes. When there is a sea swell, there will be a change in the bearing loads.
Yes.
And Look, I'm sorry, I'm not criticizing. I'm just trying to have an understanding as to where we are. Like I just was trying to tell you beforehand that the naval architects and marine engineers are the best of the friends and the worst of the enemies, because the entire shaft line is actually supported on the hull, but the entire shaft line can also go haywire because of that same hull. So that's the reason I'm just trying to understand. Like the alignment of a shaft line is singularly dependent on the hull and its behavior due to changes in loading condition, the action of sea swell, the effect of full rudder, the life of vessel, and like what the chief guest Commander Raghunandan brought out, that when immediately after construction or immediately after repairs, there is a release of stresses, due to various reasons for the first time when she's floated. So all these actually affect the alignment of the shafting, which whilst an excellent step has been taken, because the first time we are using finite element analysis to predict the offsets at various loads for the first time. That's a fantastic step ahead. But I think we need to probably take these also into consideration, so that the alignment can be robust and less susceptible to unaccounted disturbances, right? And one more thing, what actually I had discussions with my naval architect counterparts. The whole ship structure is conventionally analyzed as a rigid beam. In reality, they do undergo deflections due to the effect of various factors. These apparently minor deflections in the centimeter range have a profound effect on the shaft alignment and bearing clearances, which operate in the 10th of the millimeter range. Like the shaft deflections, hull deflections are probably in the centimeter range, whereas the shaft alignment requirements are in the 1/10th of a millimeter range. Yeah. So I think this is where the gap is. If this gap can be filled, probably it is done. And also, whilst the shaft alignment is analyzed through the finite element method, the hull deflections still follow the conventional and empirical routes. What is your take on that?
Sir, I appreciate your concern. Actually, we have used analytical method because we are dealing with very less domain. So when we are a PSI or propulsion system integrator, like a consultant designer, then we should do the hull deflection, means finite element analysis of hull structure, and incorporate these values at different loading conditions. As even whatever I have presented is only cold static alignment, sir. There are many conditions like hot alignment conditions are there, which are given by OEM. We need to go a long way towards that. Definitely, we'll go with your support.
So the one more thing is that whilst prediction of hull deflection based on the prediction from the Viva software is indeed a fantastic step in the right direction. Like you rightly brought out, I think we need to still walk along a little to capture the complete ambit of static and transient, both transient and dynamic disturbances.
Yes, sir.
And more effective ways of monitoring hull deflection. I feel that probably to complement the jack loads in afloat condition, we also need to, in afloat condition primarily, like you like to split it into two parts. One is in afloat, you did bring out, telling that we use the jack loads, whereas then we come to the dry dock and we see the bearing clearances. Now, is there a way of, let's say, checking something in afloat condition also? People talk about poker gauges, but can we measure the what do you call the stuff, the loads or the deflection in the underwater condition?
So it is very difficult.
It
is very
I
difficult.
Like to also share with you.
We have tried this, but how to measure inside that stern boss? So it is a challenge. Stern boss, stern tube bearings.
Yeah, especially the forward one, because the deep sea sill is difficult to open up also.
Yes, sir.
One more thing I'd just like to share. In certain shipbuilding practices, there is something as a load dynamometer, which is actually a dynamometer. So the jack loads, the bosses, the A bracket and B bracket bosses they're threaded, and we actually hoist we put the dynamometer from down below with the dial indicator on top. And this is done for overboard, that's outboard bearings also.
Okay.
The jack loads, whilst you may agree with me that both in the shaft designer or the conventional softwares, the jack loads are given at each bearing. We can actually find out. So probably a check to, but in Indian shipbuilding practice, I think we don't use this system of checking the jack loads from the outboard bearings.
Yes, sir. We don't
Probably
use.
we could have a look at it. That's one thing.
Okay.
Then the next point I brought out is that the class has introduced something known as the enhanced shaft alignment notation by the American Bureau of Shipping, and there's a BVQI rule note on the elastic shaft alignment, both of which actually mandate analysis by FEM. As Mr. Dasgupta had brought out, in the initial discussions, that we need to look at, let's say, after the engine room, that the entire thing, the FEM analysis needs to be done. So this, I think the classes also introduced this, but I think probably the class could also consider introducing integrated rules for use of finite element analysis, fluid structure interaction, and computational fluid dynamics for prediction of hull deflections.
Yes.
Now, as a natural corollary, if this comes in, these software applications, they could also be used for optimization of hull design and health monitoring. Hull design is some aspect, probably we still like conventional, as discussed earlier also, we still follow conventional rules. But probably once the software applications see greater usage, we'll be able to optimize the hull design itself and also for health monitoring. And I think these are well within the capabilities of contemporary software and hardware. Would you like to comment on that?
Yes, sir. This is well within the limit, but it is a time-consuming process. So,
but how do you think we should, the Indian shipbuilding industry, how can it actually introduce? Or is it first of all, actually correct to get into it, or do we go ahead with what we have got?
Sir, in this environment right now, we are having OEMs for all these activities, means for shafting calculations and all those. Once it is taken up by some firm or indigenized, I think all the activities that are mentioned by you, like FSI, fluid structure integration, computational fluid dynamics for optimizing hull forms, and also for this shaft hull deflection values at different loading conditions. This can be taken, and it is possible to undertake, sir.
Finally, of course, my last observation, the recording of hull deflections, namely deck breakage and aft stern drop measurements, is currently restricted to construction stage. I have not seen many ships, actually facing these sort of, being subjected to these sort of things. There's some new thing which I just had come across. Something was long base strain gauges. They have been recently introduced to monitor the health of hulls. It's known as a long base. It's, I think, 1 to 2 meter long. It's a strain gauge. It's got a long base and it's got a strain gauge. And it has been primarily introduced to monitor the health of hulls in the civil sector. So we could probably think about introducing them in the warships so as to monitor the dynamic and probably real-time deflections of the hull. So like you rightly brought out that we need to look at different solutions. We need to get probably Commander Raghunandan's expertise, his field, that is, get instrumentation into it to see, can we monitor the hull deflections and real-time, dynamic and real-time hull deflections? Is it possible? Because and further, we also need to gravitate to predict these values during the design phase itself. The design phase itself, I should be able to tell that in so-and-so sea swell, or in so-and-so rudder, or in this sort of a condition, this sort of a temperature, these are going to be the values. So we should probably get into prediction, so that and then they could be validated, doing measurements both in dry dock and service conditions. What is your take on this?
Sir, actually, hull monitoring system in the seawater environment, I am not much aware of this. Perhaps Raghunandan sir maybe throw more light on this, because what we even for condition monitoring of underwater bearings, sir, I was trying to search for monitoring the condition of the bracket bearing.
Yeah,
so
there
are talks about that, but no.
There is a system, which is given by some OEMs, bearing manufacturers, that we have something as an orbit analysis which is done. We have a proximity sensor which is which records the orbits when the bear shaft is rotating. But I thought something inside the ship, if we can monitor the hull and see how if the hull can we record or can we measure the hull deflection. And it will only come in if I can do a finite element analysis in the initial stage. I predict, consider the loads, I predict what are the deflections, and then after that, have a suitable instrumentation solution. I think that probably will be able to take it. But then we have got I think the Institute of Naval Architects who could kindly think about it as the Chief Commander Raghunandan sir, you got something to say?
Yeah, the hull stress monitoring software is already available. It is very much a product and very much in use on in the commercial sector, particularly so now that the VLCCs and such kind of large container carriers which are there. So hull stress monitoring is one of the key aspects in this, and there are established players for this. And if I recall a few years back, there was a thought in the Indian Navy also to, introduce these kind of things for some of their ships. I'm not really sure where the project is today, but I was very much actively a part of that proposal or some, fact finding.
Can that be used to measure the deflections? Hull stress is one thing. Can that be, let's say, extended to use hull deflections?
Yes. These sensors are located at a strategic, bulkheads. At several bulkheads, they are located, and there is a more of a. These are more data points, and then using these data points, there is a model, and that model analyzes the various deflections and stresses that the hull is undergoing, particularly at various loading conditions. So it is available. These products are very much there in the industry, and there are various types of use cases for those kind of solutions. How do they align with our requirements, and those kind of aspects are something which we will have to decide. Whether meaning if we want to implement such a solution, whether the economics or the need for that, particularly so when if you are using higher factors of safety, you may not even go into certain regions at all. So to summarize, these technologies are very much existing already in the market. It's only at the adaptation to our requirements is what will be the question.
May I kindly request Mr. Dasgupta, the president, to share his thoughts?
Thank you. Thank you so much. I think there are a few questions from
yes, sir,
many of the members.
So we will take them, sir. Once we finish with the panel, we will allow them.
No, I just have a few comments to make. It was kind of nostalgic for me because I was in the design office in Mazagon Docks, and we had to come down to witness the hull drop calculations during the construction stage at 3 o'clock in the morning, as you rightly said, or 2 o'clock, or around that time to do that. So it was, I could remember that. Second point is, as the Institution of Naval Architects, we strongly feel that if something is being given by the OEM, then the Indian design organizations and Indian shipbuilding community should also have the capability of performing that or doing that to cross-check, at least with regard to what OEM has given. So it is an essential need for us, either through a classification society or through any research and development institutions or a software provider like TCS. So it is necessary for us at the shipbuilding level, also during the ship repair. It is necessary. It is necessary to have that. There is a third point which I would like to request Mr. Raghunandan to comment on. This is with regards to the, in most of the cases, your naval ships and many of the ships they have got double propellers. You have a dual shaft system. In case it is a fixed pitch propeller, normally your propeller rotation is outward. Whereas in case of controllable pitch propeller, your shaft rotation is inwards, normally, your propeller rotation. So this, does it affect, or to what extent it affects the entire analysis of the shafting system? And is it necessary for the ship designers, from the naval architect's point of view, to incorporate this in terms of, if there is any change because of that, to in the design of longitudinal partitions, to ensure that the loads are properly distributed and the loads are not coming on the shaft and the bearings?
Sir, may I answer this question?
Yes, please. Of course.
Yes.
Of course.
Sir, actually what I have presented is only cold static alignment condition. So we have undertaken whatever the calculations that are undertaken by OEM as per his alignment calculations document in our shipyard also. So we have cross-checked and validated. That learning is also done. Secondly, sir, you were talking about inboard and outboard rotation of the propeller. So there is also one part which is called as we have the provision to input this hydrodynamic, means propeller loads in shaft designer. So that part is also done, and that part alignment calculations are also in place for inboard and outboard rotation, sir.
Okay.
For
Thank
fish
you.
pitch as well as CPPs.
Yeah, thank you so much, because I didn't know about that. Thank you.
The FEA packages available for design of shafting are pretty elaborate and actually cater for a large number of conditions. I would now like to request Dr. Bharadwaj if you'd like to comment on.
Thank you, sir. I was listening to all the valuable comments from the chief guest, from the session chair, President Mr. Dasgupta and Mr. Mahesh Kawade. Yes, it was a very practical problem, and as we always tell, there's an inside view and outside view about a ship. The marine engineers look from inside to outside, and the naval architects look from the floor to the inside. So somewhere there is always the debate between the inside view and the outside view, and propeller is one place where the views are very much, what to say, I can just put propeller as the place where the conflicts also sometimes occur, as Captain Girish nicely brought out. With respect to shaft alignment, I've been associated with the various other groups which are into, including Captain Girish's group, which are into this. And since a lot of things has been talking about condition monitoring, including at sensor level, is very much evolving. And we are no longer talking about just strain gauge based sensors, but we are also talking about fiber brag dating sensors. It is in a research stage only, but yes, we have used it in some research projects, not on ships, but on model plates and model cylinders, to see how effective fiber brag datings can be there. They're very much effective on their range, and their performance is much improved compared to strain gauges, and their insulation is very much simpler compared to strain gauges, and those all will be very much in the future. But when it comes to bearing loads and bearing temperatures, a few non-invasive methods are also there, which will probably come into, and it's about setting up a very exhaustive condition monitoring system in the ship. With all these things, there's always one point, I mean, it just occurred to me as I was hearing to all the experts here. That is about the time when the shipyards or the designers' role ends and the ship operation role starts. Mr. Dasgupta is talking about the role of INA, but here also I'd like to bring that the entire database of the operations during which we have a very condition monitoring, there should be a way by which it is channeled back to the designer. I mean, today such a way doesn't exist, because the shipyards or the ship designers end their job the day the commissioning of the ship is over. And after that, if we have a continuously condition monitoring system, that data will probably be available only with the owner. If it's commercial or a warship, it will be available with the owner. And how this is translated back into the design is a loop which has to be closed. I'm not sure whether classification societies are the way or any other ways out there to close this loop. Otherwise, the condition monitoring data will not be very useful when we do such things in the future. That's my take and comment, sir. That's it. Thank you, sir.
Oh, very nicely brought out this one. But so what two important things which emerged, I think, is one is we need to build up on the capability of the Indian industry or the Indian stuff to basically cross-check what the OEM has given. And so how do we do it? How do we translate it back? I would take one step forward, not only the shipyards, but how do we go back to our schools and institutions? How do we take it back so that this loop gets completed right from the education stage itself? So once your education gets covered, then your class gets covered, your designers get covered, and the operators gets covered. I think the entire loop is very important, that the entire environment is addresses this part of it. Having said this, now I will actually, now we can move on to with the audience, with the participants. There are a large number of questions. So we can start right from, there's a question, the first question. You can kindly unmute Mr. Shashank Mishra. He talks about generally the alignment is undertaken after maturity of hull is achieved. In this process, how do we ensure that? I think he talks about, telling that, once the hull achieves a certain position. Yes, Mr. Shashank, could you kindly elaborate?
Sir, good evening. I am Commander Shashank Mishra from Warship Design Bureau, PSI. Sir, my question is that generally we wait for hull to get mature prior commencement of the shafting alignment. Now, we are not doing that here. So, how we are ensuring that hull is getting mature? That is my first. That is my first question. And second part of the question is that regarding hull deflection. Hull deflection values are largely dependent on the weight distribution. Shipbuilding is a very complex process where monitoring and controlling of weight distribution is a very difficult task. But here we have to do it. So, is there any innovative method or any new method which we can introduce for doing so? Because it is related with shaft alignment.
Look, I think the first part of it, Mr. Kawade very clearly brought out that the entire exercise today is based on a certain assumption. Now, that assumption is not catering for the so-called maturity. That's the hull to take a particular shape. He very clearly brings out that it's based on the displacement of the ship at various conditions. So when you have a light displacement ship, in sense not light, a ship in dry dock, he's now assuming that the ship is actually at 85% load in water, and based on that he goes about and he aligns the jack loads and he gets the gap sag, everything done, and he lays the shaft line. So the shaft line is misaligned in a dry dock condition, but when it reaches the final condition, based on his prediction, it is done. So that part of it is very clearly brought out that yes, it does not address the so-called maturity of the hull. I think that addresses your first question. As regards the second one, like the shipbuilding, the weights part of it, so what happens is, to the best of their ability, they try and predict the weights right from the word go, right from the design stages, right from the initial design itself. They try and predict the weight of each and every element to the last kg. And they keep, what you call fine-tuning it as the design progresses. So at the point of time when they are doing this particular activity, they take that particular weight calculations which is predicted, and they, based on that, like you brought out in the bending moment diagram, they come to the point, they come to the displacements of the at various points, and based on that, the deflection at that point, and that is fed into the shaft designer software so that we can, estimate. But yes, it's still an estimate. I think Mr. Kawade reflected.
Yes, sir, you're right. That is still an estimate. But by simulating the completed hull deflection value, we completed hull, we load various tanks to get an alignment condition. And as far as hull maturity is concerned, only after completion of major welding, the alignment starts.
I think it's okay, Commander Mishra.
Okay, sir. Thank you, sir.
Yeah, we'll go to the next participant, Komodo Bhupesh Tate. You can kindly ask your question, please.
Thank you, sir. Thank you, everybody. I have already put my questions in the box. Maybe I've just gone into a little bit of detailing as to where do you actually apply and what happens when the deck breakage values which are obtained are not within the expected estimated values. So that was my first question. And the second question was primarily the conflict which the designer will face when you see that the values obtained by the shaft designer software and what the OEM has prescribed during the process of validation, they are at difference. So which one would you go for and why so?
The first, I think the first thing is regarding the correction of deck breakage values.
Breakage.
What is brought out is what Mr. Kawade brought out. He talks about something known as an aft stern drop, which is used to identify the time at which the sighting is done. So the aft stern drop is measured, and they find out at what point it is zero. And probably that, like so he tells it in Bombay, at least it's apparently at around 2 o'clock in the morning. That it's done over 3-4 days, and at that point of time, they actually they would undertake the shaft line readings. But I presume that when you're talking about corrections, is that it is the displacement, right? Displacement of the loads at various points, which we're looking at.
No, sir, I'm not talking of the stern drop. Stern drop and deck breakage are two different things. So what I'm talking is with respect to distribution. The earlier
Yeah,
question
I think Mr. Kawade could kindly address that.
Yes, sir. Sir, these deck breakage values are just for monitoring the distortions that are encountered during hull construction phase. So taking those distortions also into account, we go for hull deflection calculations. So these are related to construction phase.
Yes, I will like to interrupt you, Mr. Kawade. I totally agree what you're saying. My query is because these deck breakages are calculated by our hull counterparts and they are estimated values. But when we start measuring them and they do not come to the estimates, where are these corrections being applied and how are they being applied? Maybe I can come down to MDL on Monday or Tuesday and sit down with you and have a direct one-to-one interaction. But that is what my query was actually.
No, I think, look, what's important out here is that they are now started using finite element analysis to predict the deflection in the hull. So if it is done correctly and if it is done completely, that as of now, they're still in the initial stage. So the prediction becomes a little difficult. So with the FEA, I think all these things they can easily predict. You will be able to actually predict how much is the distortion. And that distortion, when you're talking about deck breakage, he talks about a hull distortion. The hull distortion ultimately is what, like the earlier participant had brought out, if you try and link it up. If the hull distortion talks about, or we are trying to tell that, okay, at a particular point, this much of distortion is taking place because of hot work or because of addition of weights or because of various environmental conditions. So the prediction of that is still a criteria, is still an issue. So I don't think that is still being covered in the present situation. Now coming to the second question, that is in case of difference in values. Yes, the shaft designer, as of now, like what Mr. Kawade brought out, in fact, I think MDL has just got into the business of shaft designer in greater detail now. So as of now, the OEM is sending the shaft design reports, and at various places, in fact, in NSTL also, we are doing a second check. We are trying to validate the shaft designer software, the alignment readings, and then we try and get it to the T possible to whatever he has told. If there's an issue, in our case, I do not know about him, we always go back to the OEM and we ask him a query. We sit across a table, we understand what it is, and then we go with an agreement. Yes, both of us in the same platform before we move ahead. I think that sort of discussion has started. But like the president brought out, that it's important that we develop more of such capabilities so that we can be more confident when we make these things, because there are only 2 or 3 softwares which are used, and the OEMs also by and large use the same stuff.
Yes.
Thank you, Kawade. Next, we have got Captain Manoj Samadar. Please go ahead. His questions are, I'll just read it out. Can you please explain how the gap sag values prescribed for alignment can be implemented in dry dock condition? Isn't the gap sag values going to be different? How do we get these values out there to ensure that the alignment is good for all loading conditions?
Sir, actually, gap sag values are required for certain kind of shafting. If underwater bearings, inside hull bearings are not many, but in our case, in this case study, we have inside hull bearings, 2 and 5 bearings are there. So we do the gap sag values as per the alignment condition, and then we measure the bearing loads. If bearing loads are as per the OEM calculations or as per our shaft designer calculations, then we say that the alignment, the shaft is aligned as per OEM requirement. Elastic line is achieved.
I think I would like to add on, the gap sag is to actually have the preliminary shaft line,
Yes.
which just tells us, okay, how to, before we do not know where to place the bearings. So just gives an initial estimate of where the bearings are to be located. The minute the shafts are connected, the actual alignment is by the jack loads on the individual bearings. So I think, Captain Samadar, is it okay?
So Captain Samadar mentioned in the later part of the Q&A that his mic may not be working. So I think he may not be able to speak. And he has a few more questions, I think.
I hope this addresses his issues. And yeah, we'll go to the next person.
A few other questions by Captain Samadar.
Yeah, I will read it out. If you do go ahead with the alignment in dry dock based on bearing load examination in static condition, how can we be sure that the bearing loads and the load distribution remain satisfactory during the hot running condition? I think what Mr. Kawade brought out time and again is that they do the alignment of the bearings, assuming that the ship is in water in a hot running condition, taking everything into consideration. Those bearing loads and considering the offsets, the bearing offsets, which are bearing offsets are given, and those bearing loads are then taken into consideration. So it will be misaligned in a dry dock condition, but it will be aligned when we assume it's a fully loaded condition. I think Mr. Kawade, is that what you were trying to do, right?
Yes, sir, you're right.
So we'll go to the next question. There is some anonymous, what type of ship is considered for the study. This is a standard ship. I think we can just leave it at that. Mr. Nation George, he's got a point, line boring or chalk fasting better. You would like to, can you kindly, yes, Mr. George, please go ahead.
Am I audible, sir?
Yes, you are.
Yeah, which one is better? Generally, in some specific owners are asking for line boring. Generally, what we are doing is going for chalk fasting.
Sir,
which organization you are from, Mr. George?
Advantage. I'm from Cochin Shipyard.
Oh, okay. Oh, basically, I think it's a shipyard-based practice. Like MDL may do something, the Russian shipyards do something. Nowadays, what happens is line boring. It takes a lot of time. A lot of time goes into it. So invariably, some excess green material is given in the barrels. So that is bored. Then the bearings are placed in location, and then it is chalk fastened. But this is one procedure which is followed. But of course, we need to do the shock analysis and the shock tests also if it actually withstands that. Yeah, Mr. Kawade, anything you'd like to add on?
Sir, chalk fasting is better because it saves a lot of time, machining time in case of this boring, in case of this inclined boring, because we have to align the bearing at certain angle. So inclined boring has to be done. So as for that, boring has its own advantage, as you have more green material, a little bit of misalignment during launching can be accommodated in case of this boring methodology. But if you can control the deflections during launching, then I would prefer chalk fasting is better. That will reduce your build period.
So why I asked this specific question, one specific owner, it's a European owner, is very specific about the line boring. He's not at all agreeing to chalk fasting. We do have a lot of communication, but he is not at all accepting that. That's why I put this question.
The preferred methodology is line boring. There's no doubt about that. That is a golden rule. But some people may prefer that, no, I would like to have other things. So I think we should go by what the customer wants. Yeah, okay. Thank you.
Okay, and my second question.
Yes, please.
My second question, whether all the hull works need to be completed to start the shafting, or whether some can we say about 80% or 90%, so that we can start the alignment work in the dry dock?
Sir, the installation of hull alignment is not so major thing that is to be considered for shaft line alignment. We can have counterweights to simulate the actual line of sight. So it can be started without hull walls also. But hull walls are necessary because if the ship is in dry dock, then you should install the hull walls if you have them.
So this added weight, whether a naval architect can clearly predict this hull deflection shall also be according to the actual hull structure.
Sorry, sir, come again.
Please repeat your question again.
Sir, this weight distribution. Anyway, when we are placing the weight, we are putting some cement blocks or any other additional weights. It should not be actually as per the hull structure weight distribution. So any naval architect can correctly tell this weight has to come here, then it will be according to the actual hull structure.
Yes, sir. Because what naval architect has to do is he has to match LCG, TCG, and VCG values, and accordingly he will be distributing the weight on the hull, so that your alignment condition is established.
Okay, in the afloat condition, we have to go for the 85% of the standard loading values. Then that means we have to take all the fuel and the other things.
Yes, so we'll load the fuel tanks with water ballast, fresh water.
Okay. Okay, thank you, sir.
But one thing, Mr. George, ultimately we should understand that it's between the customer and the shipyard. So all these procedures which Mr. Kawade is talking about in these sort of forums, it is more of nice to know. We need to have a written contract between the customer and the shipyard on the procedures so that there is no confusion on what is to be done. I hope that should be very clear.
Okay.
In fact, I think probably we could look at a standardized SOP for alignment process across all shipyards, which has been approved by the customer. I think also would help. I don't know how. I think Mr. Kawade could take up an initiative to prepare a standard alignment procedure, get the classification society also involved, so that we have a procedure and we can follow that. All these doubts could be answered in that rule or a standard.
Okay, sir. Thank you.
Mr. Palit next is Mr. Palit, and his question is: if it found that shaft seals are broken when ship is in service, I think this may not be actually relevant to this particular thing. So we'll go to the next question. Specifically, he's a naval architect, so I think we should leave it at naval architecture. Thank you, Mr. Palit. Second is we can go to Mr. Professor Arun Ishwara. Thank you for the presentation. You have stated alignment for 85% and 66%. How about at various temperatures that the ship may encounter? Professor, I think Mr. Kawade has already brought out, telling that this is only for catering for the displacements. It is not for catering for any other environmental conditions as of now in the current situation. So, like we already discussed, that all these things, I think we'll have to address it at some point of time. We'll have to develop our capabilities. I hope that addresses your question, Professor. Professor Arun? Okay. We'll go to the next. Please, Admiral Harish. Good evening, sir.
Hi, good evening.
I'll just read it out. Hull deflections estimated prior launch stage. These deflections influence the shaft line relatively more in case of commercial ships, which have a big difference between the deep and light load waterline. Is the use of hull deflections really relevant for warships with relatively limited difference between deep and light waterlines? How do we know the accuracy of hull deflections? Otherwise, we could offset the bearings incorrectly. What has been your experience, Mr. Kawade?
Sir, my experience on the vessel which we under construction vessel in MDL, whatever hull deflection values that are predicted, so propulsion shafting has not given any issue till date. So
no, I think Mr. Kawade, there are two questions to it. The first question is telling that when talking about deep displacement and light displacement, it is more applicable for merchant ships. Do you feel some difference in the warships also? That's the first question.
Okay.
Can I amplify my question?
Yes, sir.
You see, what happens is basically merchant ships are carrying a lot of cargo. Okay, so the ultimately the carrying capacities of the merchant ships are huge. So there is a big difference between the deep and light water load line. And if you see, the ABS has already given a standard SOP for shaft alignment. And it talks of two different methods, one without taking hull deflection into account, another taking hull deflection into account. So there are two methods available. So the question that I have is that if in the initial stages of design before, especially for the first ship when you're launching, the accurate binding weights of the equipment are not clearly available. You are making a guess. Okay. And most of the times what happens is the equipment have not arrived. So you have put equivalent weights, and most of these equivalent weights go on the upper deck. Whereas the actual, say, for example, steering gear compartment, the steering gear has not come, which is placed at a lower level. Whereas equivalent weight, you are placing at a higher level. Sometimes you would fill the liquid fill tanks, which are not a true representation of where the concentrated weight of the equipment should be. So what happens is all these builds in inaccuracies. And if the difference between the deep and light load waterline is very small, that inaccuracy could offset your bearings incorrectly. And that in the hot condition, you could have run into some trouble. So this is the question, what I have been discussing and I have been interacting with people is, and I've said, found a lot of literature on the net where it says that it's more applicable for the merchant ships. That's what I wanted to know. Have you used hull deflections on all the ships that you have built in MDL?
Sir, recently we have started using hull deflection values, sir.
So one more thing in the class that concerned ABS rule, it tells that in case the bearing loads, they differ, like let's say from the dry dock condition to full loading condition by more than, I think, 20%, then it is to be considered as a flexible hull, wherein we need to take this, the other part of it. If there is not much of a difference between the dry dock and the full loaded conditions, then I think we can consider that the hull deflection does not have any, any value or any, it does not affect. If you see his the deflection curves which are brought out in the presentation, there is a considerable amount of difference in the deflections between, let's say, the lightly loaded conditions and the highly loaded conditions. And he is not brought out, but there is an offset which he's giving because of this condition. For obvious reasons, he's not indicated specifically. But I think he is, in this particular condition, it may be valid, sir.
So what I would suggest is, I have had discussions with shafting OEMs. Maybe it will be worthwhile of interest to everybody for MDL to interact with the shafting OEMs, as we also keep doing, to know further on this, and go into little more depth on this to know what is the best thing. Because the last thing, you see, in any case, there are so many variables when you are doing shaft alignment. It's a very intricate process because you are assuming certain conditions and forecasting for what will happen in the dynamic states. And the large number of variables will influence the ultimate shaft alignment in the running condition. So it's very important that we follow strictly the procedure. In shafting, most of the problem comes up if there are any like differential calculus. When we do in 12th standard, we are told that never skip a step, you will make mistakes. In a similar manner, in shafting, one must follow these steps very thoroughly. And some questions have come as far as deck breakage and other. Those are, basically measured values to give you an idea between different ships of the same class. Are there any variations? Because if you go anywhere, you will never find what is the acceptable deck breakage value. But it gives you an idea between different ships of the same class. It is more of a, comparison between different ships of the project for you to give an idea that is some value really abnormal. But if you follow the procedures, and if the maintenance of the bearings is also done during the operations of the shafting at a later stage, normally things fall in line. That's my take.
Sir, what I would submit, sir, that the hull analysis, hull deflection study, everything is still continues to be done in conventional ways. And
No.
So if we get the
No,
finite element analysis into it, sir, I think all those things will be addressed, sir. Be the weights, be the distortions. Yes, sir.
Let me clarify to you, because I'm speaking from my old experience.
Yes, sir.
Now I'm retired, so I can't just mention the specific ships, but Mr. Kawade will understand what I'm saying. We have got finite element models where these values can be determined. Earlier days, we used to have Maestro, which we use for P17 to predict the values. So there are softwares available where with FEA, these values can be predicted. The only issue is how accurate are the inputs for because finite element is not a magical tool. It depends on what inputs you give and what output comes out based on the inputs. So if your inputs are correct, then the results will be correct. So what happens in initial phase of design is that the inputs are not fully correct, the weights, and you are only using an approximate value. So some differences come because of that. But for recent projects, those values have been given as far as I know.
Yes, sir. Sir, may I answer this question?
Yeah.
Sir, regarding this unavailability of equipment in staggered manner, like you talked about steering gear, and we keep weights to simulate the loading condition of the steering gear. But sir, what we do by putting the weight is we simulate this longitudinal deflection of the hull, so that we ensure that the whatever weight is coming in these compartments, equivalent weight is added at adequate locations to get the similar line of deflection. We have to progress with the alignment. We have to do this since the equipment is not available, sir.
No, I understand your difficulty. All that I'm saying here, there are practical differences in actually simulating the condition. We also followed one method which I could suggest is, because of temperature variations, you have the sightings getting impacted. So we used to transfer the line, take the references from solid structures, say dock walls, mark the references on the dock walls, which are not subject to temperature variations, and use them for verifying your shaft alignment. That is another way we found we had used, which was quite accurate, and we did not face any problems. So that is another way of decoupling some of the variables, because there are a large number of variables, temperature variations, then, other, when the ship gains buoyancy, the buoyancy impact, the weight distribution after the ship has assumed 66 or 85% of full load displacement, and the wave effects, etc. So it is not a very exact science, but it is, you can use certain, methods, well-established methods, so that you don't go completely wrong.
Yes, sir.
Thank you, sir.
Thank you.
We'll move on to the next participant. That is Mr. Shrikant. His question is, what are the difference in measurement noticed at 66 and 85% of the hull? I think since this is classified, we will just leave it at it. There has been some difference which has been noticed. And there has been difference. It's not that there's no difference. The second thing is that did the conditions cater for water-cooled and oil-cooled bearings also? Mr. Shrikant, would you like to elaborate?
Sir, good evening, everyone, sir. First of all, I appreciate Kawade sir's work. And I just want to know, there was a deflection that is noticed at 66 and 85. I just want only to know the difference that is there, and how much deviation, whether the accuracy of this deflection level that was recorded, is it within the tolerance? That is what I want to know, sir. And yeah,
I think this particular question you can go one-on-one to Mr. Kawade, since
yes,
we are live
noted,
here.
Sir. Noted, sir.
Right?
Yeah, noted,
so
sir.
We'll go to the next question, please.
Noted, sir. And the project is for the bearing, the type of bearing that is utilized for, because these deflections that are there that may differ from hull to hull. So is it for the water-cooled bearing or a oil-cooled bearing? That is what I want.
Water-cooled bearing.
No, but noted. I think it is open. The deflections. If you see the bearing, whether when you put a shaft alignment, that particular software, It does not actually discriminate between oil and lubricated. While some,
noted, sir. Noted, sir.
the
I
loads
just
are
want
constant.
to,
So, yeah.
no, I just want to know the project that was intended for. Thank you
No,
very
no,
much.
project, I think we leave it at it. No, the project we should not discuss. Yeah.
Noted,
So the next question we will go to Mr. Jancy Thomas. How the hull deflection post launching can be assumed only with the stern drop measurements? Does the loading variation from design displacement have a direct impact on bearing wear down? Mr. Genoy Thomas. Mr. Thomas, would you like to elaborate? Okay. So I think we'll go to the next question.
Sir,
yes,
please go ahead, Mr. Thomas.
Hello, sir. Am I audible, sir?
Yes, you're audible.
Sir, I asked this question, sir, because sir, we are taking a stand drop measurement continuously for 3 days, sir. That is a fact. But post launching, how will be able to, whether only this stand drop measurement will be sufficient to consider for that hull deflection post launching, because there will be many other variables will be coming into play. And if we see, sir, the actual calculation, which is shafting calculation, which is given by the OEM, the range of bearing reaction is having a wide range. So even if we are having a 3 or 4 mm offset in the line itself, so that in both the conditions, the values will be within the calculated range. So is it correct methodology that we are only considering the stand drop measurement and we are going ahead with the shafting alignment?
Sir, coming to your question, stern drop we are only considering for underwater shafting, to fix the underwater shafting. Optimization is done inside the hull. So inside the hull, we are doing it by hull deflection only. We are incorporating hull deflection values and getting the elastic line that is at 85% of standard loading condition.
Okay, Mahesh sir, one more question. Any variation from the design displacement, does it have a direct impact on the bearing wear down? Because this you have considered, that's why I'm asking.
Yeah, variation in displacement is variation in draft. So there is a change in hull deflection values. So whether there is impact on bearing wear down, that has to be studied in software, or that has to be investigated.
If I may, you see, the first question is, the aft stern drop reading is only to identify the time at which we need to do our sighting, the final sighting. It tells us, okay, at this time you please undertake the final sighting, right? The second is when there are bearing variations and the hull deflection is there. The bearing loads, whatever be the hull deflection, the bearing load should not go beyond 10% or 20% of what is specified as per the OEM's recommendations. So if it is within that limit, then there is no problem. But if it goes beyond that limit, then the deflection is going to affect the wear down. Now let's say, suppose the ship is, let's say, taking a tight turn, a full rudder starboard, right? In full rudder starboard, the loads which are coming because of this full rudder, there is going to be a load which is acting probably in the horizontal axis. Now that value should be less than what the OEM has recommended. As long as that value is less than what the OEM has recommended, nothing will happen to the bearing. But the minute it exceeds it, the offsets, because that bearing is getting loaded more. One bearing is getting loaded more, another bearing is going to get unloaded, and this will lead to the failure of that particular bearing. It's for that reason that this is how these things are linked. I hope it's clear.
Yes, sir.
Yeah. So we'll go to the next one, I think. Next is Professor Arun. Not there. We again come to Captain Samadar. If I understood the lecture correctly, it was stated that the optimum offset specified the bearings by the OEM are specified for the 85% loading condition. How can we implement the same offsets and connection of the shaft line? I think we have answered this. SAG specified by the OEM is linked with the optimum offset also. That is the specified. So we just like to bring out that the gap SAG is very critical for us to actually lay the initial shaft line. Once it's connected, most important then becomes the jack load measurement. . Mr. Kamal Palit, MDL builds both merchant ships as well as naval ships. Thus, my previous question was, how do we do shaft alignment, both merchant ships as well as naval ships, when the ship is in high sea and no dry dock is available near about?
So, can I request Mr. Palit to, spell out what he is asking for? Mr. Palit, can you please unmute yourselves, sir?
You're not audible. Can you please type it out? Type your question again, please.
Yeah, if he is not audible, maybe we can take the question and respond. Thank you. Thank you, sir.
We come to the end of the questions. Is there anyone else who would like to answer questions? Kindly raise your hand and we can unmute you.
We have Mr. Amarjyoti Das who has raised his hand, sir.
Yeah,
so
please,
please.
Yes,
sir, just before that, sir, Mr. Kamal Palit has also raised his hand. Sir, you can just try to speak again into the mic, Mr. Palit. Try to just hear your question. Previously, we were not able to hear you. Can you just try in the mic? Otherwise, we'll read your questions. I think so.
So we'll
Mr.
take
Palit,
his question. His question is that
we'll take his question, sir. We'll take his question.
Yeah, his question is that how do we do shaft alignment, both merchant ship as well as naval ships, when the ship is in high sea and no dry dock is available near about? The shaft alignment, when we talk about, I presume you are asking the last coupling with the main engine or the last coupling with the gearbox. Like what Mr. Kawade brought out, the shaft alignment is done inside. We connect up the shaft coupling and we measure something known as the jack loads on the bearings. The jack load on the bearing, if there's only one bearing or two bearings, it will be specified. The shaft alignment document specifies, which is the shaft alignment document is given by the designer. That specifies the loads which are to be maintained for a perfect alignment. We go and record the readings. Once we record it, we will then, and then we correct it. Either we have to shim it or we have to remove the shims so as to get the correct load on the bearings. Then once the load is adjusted, we know that the alignment is perfect. Shaft alignment is always done in afloat condition, normally. But what, like Mr. Kawade brought out, in this very specific instance to optimize on timelines, they have undertaken the shaft alignment in dry dock itself, assuming the other conditions. I think we can unmute, we can request Mr. Amarjyoti Das to kindly. Thank you, Mr. Palit. I hope we have answered your question.
Hello.
Yes, Mr.
Yeah, I just wanted, I'm a retired naval architect from MDL. I'm just saying for the interest of the people who are listening to, that if we are talking about the hull deflection, if we want to investigate how the hull behaves under a particular loading condition, it can be investigated. I mean, if the shaft deflection is something which has been given by the OEMs, let us keep it aside. But if the interest lies in how the hull flexure will be for any ship, a small ship or a big ship, a commercial ship or a warship, it can be investigated once we know the weight calculations, weight trapeziums. It may be, as Captain Harish said, it may initially be a problem, but we have done it in the initial design for smaller ships. It is possible to do weight trapezium calculations that gives lead to the buoyancy distribution. Weight minus buoyancy will give you the loading pattern. And then from that shear force, the M by EI calculations, the slope and deflection. So if a vessel is floating as a free beam, we can also do all this calculation initially. We used to do this manually 20 years ago when FEA was not available. We can do it in an elaborate manner now. For both the ship in an afloat condition, whether it's 85% or 66% is an afloat, we can do that. We can find the nature of deflection, the magnitude that you can expect right from AP to FP. Secondly, when the ship is in dry dock at any loading condition, obviously the ship is being supported in the dock blocks. So many reaction forces are acting. we know the weight and we know the reaction forces, but it is a statically indeterminate structure because there are so many unknowns, there are not so many equations to solve it. But we have now methods to calculate all these normal reactions coming from the dock blocks to the ship. So the nature of the deflection and slope of the hull in the dry dock, even on the dock blocks, can be assessed. Now, if all these values can be assessed and the naval architect who is designing such a thing has a feel of the magnitude of this particular deflections that may be occurring when the ship is complete, then we can do a real assessment of how the shaft will behave when the hull is deflecting in a certain way, whether afloat or on dry block. So I think shaft designer, at least I know that the DNV software program, which is internationally very well known, takes care of that. Once the inputs about the hull deflection and the nature of shear force bending moment are available from the naval architect who is handling this, a realistic value of deflections of the hull and how it can affect the bearings of the shafting system, whether twin shaft or a single shaft, can be assessed by this elaborate software, and quite rightly so. In fact, it has been done by various shipyards all around the world. Another thing that has been discussed is what do we do about such huge ships, VLCCs, bulk carriers, tankers, and all, where the light draft and the low draft is very different, and obviously the hull will deflect in such a way because of the weight and buoyancy distribution. But also this can be handled the same way, the way I spoke. Another thing is to be noticed is this bulk carriers, many of them have the engine aft. So short shafts, very well supported, very short segments with hardly any spacing between the respective bearings. So the possible of very huge deflections in a commercial ship of that nature is low. So that's why I think that not much of this thing is placed on the effect of hull deflections on the shaft alignment condition and the shaft behavior in commercial ships. But of course, if the shaft line is long, like in an offshore supply vessel or something, then we have to investigate like that. So I think we have the tools for all the queries that they were there about the hull deflections, and of course the shaft deflection, where everything is known by the OEM and also the shipbuilder. All these deflections, the magnitudes can be assessed, and the overall analysis can be completed in a realistic manner. Thank you very much.
Sir, I would just like to thank you for your kind input, sir. But what I would like to submit, sir, regarding the hull deflections, all these the conventional methods, the accuracy is probably in centimeters, 1 centimeter or 2 centimeters. Whereas the requirement of shafting is in 0.1, 0.2, 0.3 millimeters. When you look at the bearing clearances. Correct. So there is a gap. So we feel that, and if you go to the so-called the latest thing, that is the BVQI note of rule note of 2015, and the ABS, the latest is 2022. It talks about the conditions and why the finite element analysis is essential. More importantly, even in merchant ships, he actually tells, it defines something known as a stiff shaft, a flexible hull, or flexible shaft, a stiff hull. Either which way, he tells what are the conditions in which we actually need to, undertake this sort of an analysis. He tells that we need to essentially get into a finite element analysis. He talks about, swell, talks about effect of full rudder, effect of sea swell, changes in loading condition, amongst other conditions. In fact, these are, whilst it's a free beam, but he clearly emphasizes that we need to gravitate, we need to move on to this sort of a situation, where this sort of a analysis, where we actually bring in finite element analysis in its entirety, so that we can have a better appreciation of it. And there have been failures. I think everywhere there have been failures on shaft line bearings. Whilst there are, if we can probably put some 5 or 10 reasons to it, one of the reasons is this one. Probably 9 reasons could be others. But we are slowly now trying to, whilst we have had experiences, but we feel that this could be one of the primary reasons also. So that is the reason. I just thought I will share it with you.
In fact, I would just like to say that we have done an elaborate calculation. Mr. Mahesh Kawade also knows about it when I was in MDL, that these warship hulls are actually quite strong. The kind of material it has, the longitudinal material and the sectional hull section properties along the length from AP to FP, we have actually assessed that at various stations and modeled that and finally calculated. These are quite strong. And as you said, yeah, the deflection overall could be in the magnitude of centimeters, but if you measure with respect to AP to midship or something, but if you talk about from bearing to bearing, that segmental length, that impact of deflection will not be in centimeters, that will be in millimeters. So that is there. But of course, as we know more about the behavior of the hull, this can be actually studied by the marine engineer to get the best result, and softwares are available.
Yes. So my only submission is that we need to start using the software, not for hull design, but for aiding the marine engineers to design, to help them.
Yes, indeed. The shaft designer and the DNV program, both are actually good at it.
Nauticus, sir. We use Nauticus, sir. Yeah. No, I'm just telling Nauticus standalone, it's not adequate. In fact, in our organization also, we have started the study into development of a finite element, a finite element model of a hull. We're slowly getting into it, sir. Initially we'll be making it, and probably we will be reaching out to the Indian marine designers and the other agencies to see that they can also develop the FAM of a hull and see how we can merge and mix the Nauticus with that particular. We need to link both of them, sir. Nauticus is the one by DNV, shaft designers. Yes.
As you yourself said, that if the magnitude of the actually variations are well within 10% of the actual OEM provided values, then you should not be actually breaking your head. It will be all right.
Yes.
Yeah. So that amount of margin is available. So that's what I said, that the naval architects should actually clearly determine what kind of magnitudes of deflection the ship hull will face when it actually is in a seaway, and also when it will be in dry dock. If that magnitude is known, then possibly the naval architects and marine engineers in a shipyard will sit together and find a clear optimum solution to their problem.
Like one good indication would be the aft stern drops. Like if the aft stern drop is more than, let us say, 10 millimeters or 15 millimeters, 20 millimeters, I think there is a cause for concern. But if it's less than, let's say, 3 or 4 millimeters, then the ship is stiff, and it's rigid and it will not make much of a difference.
Indeed, all the past, my seniors and Masgon Dock who have been doing this operation for the last 30-40 years have been following exactly what you are saying.
Yes,
if it is well within a magnitude, then you don't have much
to worry
about. Right, and this 85% has also been evolved by the Russians after going through all kinds of displacements in a ship. And they have found that this particular loading condition actually simulates the toughest condition which the ship will face in a seaway in its entire life. It is very close to that. I mean, they have already investigated that. That's how we come to know. There's no rule book which says 85%. It has only come from some certain, design bureaus in Russia who have found that this particular loading condition simulates the best condition which can be used for an analysis. You can't do everything from light load to deep load. We have to arrive at an optimum condition where all investigations can be done, and that's why this 85% was found out.
Yes. Thank you, sir. Thank you.
Thank you very much.
Now for the closing remarks, I think the participants have finished their interactions. I would like the chief guest, in case you would like to comment. We got another 5 minutes now, sir, before we can close up.
Yeah, thank you, Captain Girish. And, I think much has been already discussed and debated on this. Certainly, finite element analysis methods are the way ahead to go in order to optimize the time and the cost of ship construction, particularly for critical activities like shaft alignment, which rightly Mr. Kawade is working on right now. And my only suggestion is that in this finite element analysis, as Admiral Girish rightly brought out, is just another tool and the right use of the tool is very important, because when you get into finite element analysis, there are lots of variables there. The type of the finite element that you choose, the number of elements that you choose, these make a big difference in the results that you will get. So whatever the assessments that we make, that we have an 85% or all these kind of confidences which we have, that when we complete the job in the dry dock using these advanced techniques, we have to realize that at the end of the day, we are trying to make a highly non-linear system into linear, because that's what man realizes ultimately. Like I just had to quote here from one of my professor, mathematics professor, that the only thing man knows everything in the world is to add and subtract. He doesn't know anything beyond that. So whatever we may face in the world today, whatever issues, particularly a complex activity like shaft alignment, you have to find some methodology to bring it to do 2 + 2 or 3 - 2. That's all what you have to do, so that we understand what we are doing and we are confident that what we have done is the right thing, and there'll be no looking back. And I'm very sure, as also one of the other speakers brought out, that MDL has a very, I think that was Mr. Das, that MDL has a very solid history, even before these finite element methodologies were there. I think there has been, I do not recall any ship where there were shafting problems ever, which came in, even when, the very first trial, the ships went out to sea with on full power. And I think there are ample examples, at least as a Navy person, and Admiral Girish, Harish, who is our guru actually in all these matters, we have achieved quite a bit of success, even with 100-meter shaft lengths. And I'm very sure that the work you are doing is the step in the right direction, and all the very best. And hopefully we will see ships rolling out more faster with this kind of methods. Thank you, and very great job done.
So now I look the Mr. Dasgupta, sir, if you've got any comments.
Thank you very much for the lovely session, actually. And we are really fortunate to have comments from Admiral Harish. Mr. Palit's comment is possibly related. I would like to comment on his question, and elaborate on certain issues slightly. And also Mr. Das has pointed out the experience and the capability of Mazagon docks and what the naval architects can do with regard to integration of the hull and shaft alignment. In case of ships, especially for big ships, which in most of the cases, they have their, the entire engine in the aft and very short extent of the shaft line. We have situations in which the repairs are carried out afloat, including the propeller unloading, loading, and propeller change, damage repairs, in which the ship is trimmed forward and the shaft line is brought out. And we have cases in which the shafting was, the shaft was taken out, the bearing changed, and then put back. And that is the time when the shaft alignment also needs to be checked. So this is a case for commercial big ships, where typically the case of bulk carriers and tankers sometimes, where the situation is very different from what is happening in naval ships. I have a very naive question to you all. Considering the situation here, we are all talking about finite element analysis, and we know the implications with regard to choice of correct element choice and all that. I was wondering, for a smaller ship, or a ship which is a shorter shaft length, can we not have a small finite difference analysis instead of FEA, FDA, and then utilize that with a good GUI and give it out to small ship designers and shipbuilders? Because we may not really need to have a finite element analysis for that. Because it is essentially a continuous, multi-supported beam solution, for which we also have solutions, hand solutions. Originally, what we used to do with SAGs and all that, and also with regards to the finite difference calculations, which were being done before the finite element came into it. Now, for shafting system design for smaller ships, can we not have a small finite difference analysis program dedicated for smaller ships, and can be given out to shipyards for them to utilize it? Would there be any really bad implication on that? So with that, I would like to close my comment. Thank you.
Mr. Kawade, anything you would like to further sum up?
So you have asked me?
Yes, Mr. Kawade. Sorry, Mr. Mahesh Kawade. If you got anything else to sum up, please.
Sir, thank you. I presented the case. Thank you for giving me an opportunity from Institution of Naval Architects. And I am very happy that Das sir was there to hear the presentation, because he is aware of the entire thing. And he's our mentor at that time. He was also a guiding force behind all this. Thank you, sir.
Dr. Iyengar, if there's anything you would like to sum up your stuff?
Just summing up, sir, formally, I'll just come later. There are some of the things, for example, to answer Das Gupta's question. I know there are research projects in IIT Kharagpur. Some young faculty is trying to do the finite difference method, including seakeeping for hull deflections. Now, there was another very young faculty who has just completed some research on a different topic. We are trying to motivate him whether he can join hands with other faculty so that we can also consider shaft line and bearings. In fact, we are hoping to seed some academic programs which probably will not develop a GUI, but probably will go in some direction that later, a couple of years down the line, we can actually make it into a GUI with a company. We are knowing that a small group in IIT Kharagpur is working on that, sir, just to add to your points.
Very nice. Thank you. Thank you for very good.
So thank you one and all. It was a very interesting session. I would just like to sum up very quickly. So the major points are that yes, finite element analysis is essential. If we could have instrumentation to monitor hull deflection, why not? We need to develop indigenous capabilities to cross-check and to understand what the OEM recommendations are. We need to channelize back our experiences to design organizations and to the shipyard, to the institutions that teach us. We need to understand the magnitude of what it is and how it is. We need to understand how to convert non-linear to linear. We need to undertake a system level analysis, basically to whether the requirement to go in for more detailed process or is the process adequate. That's for every ship. Probably we'll have to do a small system analysis before we like to invest our resources. A standardized SOP for shaft line, probably the shipyard MDL could probably steer this process and share like what Mr. Das Gupta brought out. We could probably have a standardized SOP also, which could be shared with all the Indian shipyards so that we have we share our knowledge levels. We need to settle a process probably for jack load estimation of external bearings. And finally, we need to have an FTM model for smaller ships, which could be shared with anyone. And probably we could, make models. Finally, we could have different models of different sizes and different dimensions: slender ship, normal ship, big ship, small ship. We could have models of each of them wherein we undertake this entire process run through the entire process and have them as case studies. So I do not know. I do not know whether it's the Institute of Naval Architects which could take up all these things to the next level, whether they could coordinate such activities and motivate our education institutions, our the shipbuilding organizations, the marine design organizations, the Indian marine design organizations, and other such institutions. If the INA could kindly take it up with them and see if some of them at least are addressed, and so that we can take it forward. So thank you for giving me this. It was really been a privilege and honor to be a part of the session chair for this thing, which is very close to my heart. And somehow it so happened that it fell into place. Thank you one and all for the active support and participation. With this, I would like to hand back to the technical secretary for final closure. Thank you, sir.
Thank you, sir. Thank you, sir. It was a very lively session. Ably participate. We had at one point of time we had around 90 participants joining this lecture.
Initially I had asked Dr. Bharadwaj how many people attend this sort of lectures. He told 40, 50 is a figure. So 90 is a good figure.
Yes, sir. Yes, sir.
Even the topic and Mr. Mahesh covered it.
Yeah.
Very interesting.
Yes, sir. My first thanks is to Commander Raghunandan, who ably was the chief guest for today. As soon as we invited, he accepted it, as well as from his opening remarks to his mid remarks and conclusion, ably added to his knowledge and wisdom. I thank Commander Raghunandan. Captain Girish, the session chair, has ably steered the session. In fact, he was also answering most of the questions, and the Q&A was also made very lively and actually converted the Q&A into a very nice panel discussion. I thank you for that, sir, as well as ably chairing and bringing your experiences and wisdom. When I read the bio sketch, I just told that he deliberately wanted to be brief, but during the Q&A session, we just understood the breadth of his experience. Thank you for ably chairing the session, sir. And my thanks to Mr. Mahesh Kawade. When I had this discussion with him a couple of weeks back on the topic to be discussed, there were a couple of options. As we see in his CV, he has also worked on CFD and all those things. But finally, he chose this topic, and it happened to be a very lively and practical, of very practical importance. And so I thank Mr. Mahesh Kawade for both choosing this topic, as well as initiating a very good lecture, which gave a lot of food for thought, even for future actions. With that, I also thank all the participants of the lively Q&A session and the senior professionals. And this time we had Admiral Harish, Mr. Amarjyoti Das, Commodore Bhupesh Tattar, Mr. Palit, and all senior professionals who added their wisdom to the Q&A session, as well as very practicing professionals who also added a very lively Q&A session. I thank all of them for bringing the experiences, asking the right questions, and enriching the whole lecture. And finally, as I started this vote of thanks with the participants, 90 participants, a very good number. I thank all the participants for taking the time on a Sunday and joining this INA lecture. For the information of all the participants, this INA lecture is available on YouTube. The link was in the chat box. Otherwise, also you can just search on YouTube INA Indian Institute of Naval Actors in the YouTube. There's a YouTube channel where all our previous lectures are also there, and I just request all the audience to watch it and get enriched and advise us. Thank you, sir. With this, we can conclude the session. Thank you. Thank you all for joining us.
Thank you. Thank you.
Thank you.